Welcome back to 8 Minute AI. Today, let's all make a smart move and go back in time, back to our second episode where we defined machine learning. A listener asked how Arthur Samuel's checkers program actually worked, so today we're diving in.
And if there's a topic you'd like us to cover, feel free to drop us a comment or message us on LinkedIn. We love taking requests.
All right, quick refresher. Machine learning algorithms learn from data, improving performance over time as they process more information. One of the earliest examples of that idea came from Arthur Samuel in the 1950s. His checkers playing program learned by playing games and adjusting its decision based on which moves led to wins.
Last week, we talked about reinforcement learning, which is training through feedback from actions and outcomes. Instead of single correct answers, sequences that led to success are rewarded. Samuel's machine worked exactly that way. Each move wasn't graded on its own. The win at the end reinforced every move that led there.
Think about how you play checkers. You study the board, list your possible moves in your mind, and then you try to predict what your opponent might do next. That loop, observe, plan ahead, and act, that's exactly what Samuel's program did.
It relied on two main tools. One was a scorecard, the other was a look ahead. The scorecard rated how good each board position looked. The look ahead explored several moves into the future, assuming the opponent would reply intelligently.
Picture a checklist with point values. More pieces are good, more kings, even better. Safe pieces near the edge, good. Control at the center, also good. Add up all those little bonuses and penalties, and you get one number, the program's guess at how favorable the board is for the current player.
So, where did those point values come from? Samuel gave the program a scorecard to start with. This was based on a book called Lee's Guide to the Game of Checkers, and that book was from the 1800s, which is basically like a book of cheat codes for gaming. The book gives annotated example game scenarios and then the best and worst moves to make, along with the game outcomes. Think of this as a supervised learning phase. Then the program began to improve by playing more games.
After each game, it nudged those point values. If a feature tended to appear before wins, that feature's score went up. If it appeared before losses, its score went down. It also kept a small notebook of board positions it had seen before, storing which move had worked best. When the same situation appeared again, it could reuse the stored move instead of recalculating everything.
On every turn, the program didn't just look at the current position, it looked a few moves ahead, assuming the opponent would play optimally. You don't want a move that looks good now but falls apart after your opponent's next move.
It compared those future positions using the scorecard and then chose a move that left the best score in the worst case scenario.
That strategy has a classic name, minimax. You try to maximize your outcome while the opponent tries to minimize it. So you choose the move that minimizes the maximum damage your opponent can inflict.
The trouble with looking ahead is the number of possible positions explodes, like branches splitting into countless twigs. Samuel had a clever shortcut, though.
While exploring, the program skipped any branch that couldn't possibly beat the best option found so far. If a path was not as good as your current best, then there was no reason to keep going down that path.
That trick, now called pruning, lets the program search deeper without extra hardware. Think of it as saying skip any move that can't win. It pairs beautifully with the minimax idea.
So let's walk through one turn. Step 1, list every legal move. Step 2, for each of those moves, imagine the opponent's best reply, maybe even a few replies deep. Step 3, prune branches that can't change the outcome. And step 4, pick the move with the best worst case score.
That best worst case idea can be confusing. You're taking the best of the worst case scenarios. So it's not which move captures the most pieces, it's actually which move keeps my opponent from capturing me later. It's a defensive thought process.
Exactly. Oversimplified, yes, but that mindset is what made the program strategic rather than reactive.
Then, when the game ended, the learning step kicked in. The program reviewed every position it saw and asked which features showed up before good outcomes, nudge their weights up, which showed up before bad outcomes, nudge their weights down. It also added new positions to its notebook for the next time.
Those updates didn't rely only on the final win or loss. The program also noticed how the score changed during play. So if a move led to a position that looked better, according to the scorecard, that was positive reinforcement. If it looked worse, then negative reinforcement. Tiny adjustments like these accumulated over hundreds of games, stabilizing the point values.
So Samuel's method was a type of reinforcement learning. The feedback came at the end of each game, depending on the win or loss, which would then adjust the values to the positions played during the game.
Why not just store exact win-loss counts for every position? Because exact repeats are rare. There are roughly 10 to the 120th possible checkers layouts. Far too many ever to see twice. The scorecard lets the machine generalize patterns instead of memorizing boards.
Yeah, that generalization is the key. The scorecard's features capture broader lessons: formations, safe zones, and control of space. Even if the board was new, those same ideas still mattered.
It's a lot like human learning. A beginner focuses on captures, but a seasoned player recognizes when the formation on the board is strong or weak. So you're not adding up numbers, but you know that a compact center formation is safer than having scattered pieces on the board. Samuel's program just formalized that instinct with math.
And remember, this was the 1950s. No GPUs, no cloud computing. The look-ahead depth was only a few moves, but with pruning and a good scorecard, it reached a strong amateur level.
You might wonder, if the scorecard works, why keep that notebook at all?
For two reasons. First, certain board setups, especially the start and the end of the game, those setups tend to repeat often. If the program already knows a good move there, then it can reuse it immediately. Second, the notebook can store tactical tricks that the simple scorecard doesn't fully capture.
It's a tiny specialized memory, not a replacement for general reasoning. Think of it as an index card for special cases.
Samuel built and refined this system through the 1950s and 60s. His program learned by playing both humans and itself. On that mid-century hardware, it became impressively strong.
In public exhibitions, it could challenge skilled players, and it even played matches by mail against top competition.
Snail mail, that is. Email didn't exist yet.
Can you imagine how long those games took?
Samuel's checkers machine wasn't just a novelty. It planted the seed for self-improving systems. That same learning loop shows up everywhere today.
It's the process of rate, look ahead, choose, and learn. Whether it's a self-driving car evaluating turns or an LLM deciding which sentence sounds best, the process is the same.
If you listen to our last episode on how AI models are trained, this might sound familiar. Samuel's initial scorecard was like pre-training, a foundation of basic knowledge. Each game it played afterward was like post-training with reinforcement learning, fine-tuning those weights with real feedback. Even back then, the blueprint was the same. Start broad, then refine through experience.
So even in the 1950s, Samuel's checkers player demonstrated the core ideas behind today's AI training, like supervised learning and reinforcement through rewards, all in one system.
His work proved that machines could move beyond fixed rules and learn from experience. That insight eventually inspired everything from modern reinforcement learning algorithms to today's generative models.
So next time your favorite AI beats you in a game or finishes your sentence, remember Arthur Samuel's checkers player. It was one of the first programs to show that computers could teach themselves to think ahead.
Oh man, next time I play checkers, I need to start thinking further ahead.
Thanks for joining us today. If you like this episode, please consider giving us a 5-star rating and share the podcast with other curious minds.
Give us a follow on LinkedIn. If you have a question about AI, send it our way. We may feature it next.
Catch you next time on 8 Minute AI.
Bye.
Bye.